Hi everyone! Today let's talk about sessions 11.4, Boolean functions and synthesis of circuits. So let's look at this logic table. Do you remember we talked about the exclusive OR? So exclusive OR means we have to pick either x1 or x2, but we cannot pick both. That's why when x1 and x2 they're both 1s, x1 exclusive OR x2 is gonna be 0. Okay, as long as exactly one of them is 1, then we get 1. Otherwise is 0. Okay, so that is the exclusive OR. So a logic table, we have some inputs and we have one output. So this is actually a function. The domain is the set of inputs and the range is the set of outputs. For the exclusive OR function given in the table, the domain is the set, the order pair 1, 1, 1, 0, 0, 1, 0, 0. Okay, and the range is the set Z2. So Z2 we denote is the set of consists of two elements, 0 and 1. If we can develop a formula for the exclusive OR function of the form, so the exclusive OR equals a function, a Boolean expressions of x1 and x2. Then we can construct the combinatorial circuits corresponding to the Boolean expression. Okay, so definition, let x be a Boolean expression, a function f of the form f of x1 xn equals the Boolean expression applied on x1 xn. So the f is called a Boolean function. Alright, so let's look at the following example. So the function from, well, this notation means we have the Cartesian product of Z2, okay? So we have three inputs, three variables, okay? So, or we can say we have three coordinates, x1, x2, and x3. Okay, so this is the function f of x1, x2, x3 equals x1 and parentheses, not x2 or x3. So this is a Boolean function. The inputs and outputs are given in the following tables. Okay, so we can check why we come up with this table. So let's see, x1. So if x1 is 0, then all of them are going to be 0, right? And then for each of them, if x1 is 1, then okay, 1 and whatever is that thing. So then this guy is not 1 is 0, 0, or 1 is 1. So 1 and 1 is 1. Then here we have not 1 is 0, 0, or 0 is 0. 1 and 0 is 0. Then here not 0 is 1, 1 or 1 is 1. 1 and 1 is 1. Here 1 or 0 is 1, 1 and 1 is 1. So far so good. So this is how we get the logic table. So questions. Given a function with a table, how do we find a Boolean expression associated with it? Okay, so in our previous example, we were given the Boolean expression and we can come up with the logic tables. But right now, if we're given the logic table, how can we find a Boolean expressions associated with it? Okay, so this is how it works. Step 1, we want to search the output with 1. Okay, which one are the lines such that the output is 1? So with this guy, and this guy, right? This is step 1. Then step 2, go to that row. Okay, with the output 1, and then we can construct a Boolean expression for that row. Okay, so if you see 1, use x. If you see 0, use not x. Okay, so let's look at the first one. You see, all of them, x1, x2, x3 are 1. So this guy corresponds to x1 and x2 and x3. Okay, so we use and to connect them. And then this guy, you see x1 is 1, so we have x1, but x2 and x3 are zeros. So we have not x2, not x3. This guy, not x1, x2, not x3. So far, so good, everybody. Okay, so use and to connect them. Okay, this is step 2. Then step 3, finally, or. Use or to connect the terms or expressions from step 2. So that's why our final answer is x1 and x2 and x3, or x1 and x2 and not x3, or not x1, x2, not x3. So this is our final answer. This is our Boolean function. So far, so good, everybody. So this is how, when we're given a logic table, how do we come up with a Boolean expression associated with it? Okay, we look at the rows with the output 1, and then for each of them, we look at the inputs. If it's 1, we use x. If it's 0, we use not x. Okay, and then we use and to connect them to create Boolean expressions for that row. Finally, for different rows, we can use the or to connect them. Alright, let's continue. Okay. A minute term in the symbols x1, xn is Boolean expression of the form y1 and y2 and yn, where each yi is either xi or not xi. Okay, so those are the meaning terms. You can see all of our so all of these guys, they are mini terms. Okay. Next, we have a theorem. If f from z to n, so this is a Cartesian product where we have like n coordinates. Okay, so to map to z2, if f is a Boolean functions, if f is not identically 0, we can let a1 8k denotes the element ai of the z to n, for which f of ai is 1. For example, ai could be like a1 an. So this a1 an, it could be some numbers between 0 and 1. Okay, so it's either 0 or 1. Okay, and then mi is y1 and yn, and hyi is either xj or not xj. So if it's xj, then if aj is 1, we denote as xj. If aj is 0, we denote xj bar. Okay, then f of x1 xm is gonna be the m1 or m2 mk. So all of the mi's are the meaning terms. So like our examples, each row, so the meaning terms correspond to each row. Okay, so corresponds to each row. Okay, each row with the output 1, like our previous examples. And then you figure out the meaning term for that row, and at the end you use or to connect all of them. So far, so good. Okay, the representation of a Boolean function in this form is called the destructive normal form. So remember, disjunctive means we use or. Okay. Next, let's look at our example. Let's design a combinatorial circuit that computes the exclusive OR of x1 and x2. Okay, so first step, let's figure out which one has the output 1. Oh, those are the two rows, right? This guy, we have x1 is 1, but x2 is 0, so we have x1 and not x2. And then this row, we have not x1 and x2. Okay, and then finally, we use OR to connect them. So that's x1 and x2 bar, or x1 bar and x2. Okay, so this is the Boolean expression. Alright, so with the Boolean expression, then we can use a combinatorial circuit to express this one. Okay, this exclusive OR. Okay, so how does that work? Well, we start with x1 and x2, right? And let's look at this guy. This guy, x1 and not x2. So not x2, the NOT gate looks like this, right? Let me recall you, this is the NOT gate. This is the AND gate. And then this guy looks like a fish, is the OR gate. So far, so good. Alright, so x1 and x2 bar. So this is NOT gate, and then we use it to what? AND gate looks like this. Okay, and then next one we have x1. Oh, okay, with x1 bar. What x1 bar means, we need to have something here. So let me do it like this. Okay, and then this is x1 bar. We also need x2. So let's do x2 here. Sorry. So go around here. Okay, so here we have AND gates, and AND gates looks like this. Finally, we have the OR gate, so like this. Okay, so this is the combinatorial circuits we designed based on the Boolean expression. So far, so good, everybody. Alright, let's continue. Okay. Wow, here we have 3 inputs. Let's see. First, we look at the rows with the outputs 1. Okay, so here we have 4 of them. And then for each of them, let's construct a Boolean expression for that row. So this one we have A is 1, good. But B is 0, so, and not B. C is 1, good. Here A is 1, but B and C, they are 0, so that's why we have AND. Not B and not C. In this guy, we have not A and B and not C. This guy, we have not A and then not B and C. So for last session we talked about our notation. We can, for AND, we don't need to write it down. So if we just put A, B bar and C, this is what we mean by AND. Okay, and then for this guy we have A, B bar, C bar. Just for shorter notation. This is A bar, B, C bar. This is A bar, B bar, C. Okay, so finally we can combine all of those rows and we use OR to connect them. So that's why F equals A, B bar, C, or A, B bar, C bar, or A bar, B, C bar, or A bar, B bar, C. So far, so good, everybody. And we can use this information to construct combinatorial circuits. And it's actually quite complicated, and because of time I already make it here. You can see here we have three, okay, sorry, here we have three inputs A, B, C, and then for each of these mini term we have something, a circuit there, and then you want to take the disjunctions or to connect them. Okay, so that is my picture. So in our exam, I won't require you to draw the combinatorial circuits for 3 inputs. Okay, so this is quite a lot. Okay, but it's okay to ask you to write down the Boolean expressions for it. Okay, but I won't ask you to write down the circuits for it. Okay. All right, let's continue. Maybe you can try to draw it. It just take more paper. Okay. Next. Ooh, this is more. You see, if there are more ones, it means your Boolean expression is gonna be longer. Okay, it's okay. Let's do it. So this guy, we use A and B and C. Okay, so right now we don't need to put the and symbol. Okay, then this guy we have A and not B and C. This guy we have A, not B, not C. This guy we have not A, B, not C. This guy we have not A, not B, C. And then this guy, all of them not. Okay, so we have 6 mini terms, and then we use OR to connect all of them. So A, B, C, or A, B bar, C, or A, B bar, C bar, or A bar, B, C bar, or A bar, B bar, C, or A bar, B bar, C bar. So far, so good, everybody. All right, and this is our F. Okay. And here, the combinatorial circuit is going to be more complicated. So last example, we only have 4 mini terms. This crazy. And then right now, we have 6 mini terms, so it will be more complicated. So let's not do it here. Let's continue. So example, find the disjunctive normal form of each function. Use algebraic techniques. Okay, so let's see, algebraic techniques, which means we can use the associative law, commutative law, distributive law, and some properties of Boolean algebra, right? So let's look at the first one. So the first one, what do we get? Okay, so this guy, we can try to distribute it, right? So let's see here. So let's use the first one, this guy, and then this guy. Okay, so this is how we distribute it. So we have x times, actually times is the same as and, okay, in our expressions, and the or is the same as plus in our Boolean expression, right? And then we have or y times x bar y bar. Okay, so this is the first step, and then we continue to distribute it. So we have x and x bar, or x and y bar, and then or y and x bar, or y y and y bar. Okay, now because all of these are OR, so actually we don't need the parentheses. Okay, and then what is x and x bar? So you can think about like a set complement x and its complement intersection is empty. So this is actually 0. Okay, so but 0 or whatever is that thing, right? And this is or y x bar, and y and y bar is also 0. Okay, so because 0 or whatever is just these things. So this is our answer, x bar, y bar or y x bar. So far so good. Okay, so this is the destructive normal form. Let's continue. Okay, so when we have x, y, z, we'll have more variables. That actually a quicker way to help us to solve the problem using like algebra, because we're more familiar with. So we're familiar with plus and multiplication, right? So we can translate the and or to, and is like multiplication, or is like plus, right? We can translate to multiplication and plus, and then we calculate using our regular algebra techniques. And then after we are done, we can change it back to and or. Okay, so also because for all the destructive normal form, you want to have the many terms contained all of the x, y, and z. So sometimes you're gonna insert x plus x bar and y plus y bar and z plus z bar, because this is like union. X and x complement union is like the universal sets. Okay, so all of these is just like 1, so we can insert it. And also keep in mind that x times x is x, because it's like intersection. A set set is that set. A set union that set is also that set. Okay, so even though it's plus, but this is special. You can think about it's a union. There's no such thing like a 2x. Okay, so x plus x is x. This is special. For Boolean algebra. Okay, now let's translate the problem, and you can see how easy it is. So x or is like plus, and then we have the y, and still and is like multiply, and then we have the x plus z bar. So far so good. So let's distribute everything. So x plus y, x plus y, z bar. So far so good, everybody. Okay, so this is destructive, but however each term, each is the mini term does not contain all the x, y, z. So that's why we need to insert. Okay, so we want to insert the y, so let's do y plus y bar. We also want to insert the z, so z plus z bar. So this is the first term. And the second term we have like x, y, but we're missing z. So let's insert z plus z bar. And then next we have the y and z, we don't have x, so let's insert x plus x bar. So far so good, everybody? Alright, now let's distribute everything. That's why it's easier to change it to plus and multiplication, because we're more familiar with that. Now, okay, hide, you use your finger, hide the y bar. So use the y to distribute. We have yz plus yz bar, and then y bar z plus y bar z bar. Okay, next we have xyz plus xyz bar, and then next we have xyz bar, x bar, yz bar. So far so good, everybody? Oh, let me separate them. So Okay. All right, let's continue. Ooh, we have to continue to distribute it. So let's see. This is xyz, xyz bar, xy bar z, xy bar z bar, plus xyz, xyz bar, xyz bar, x bar, yz bar. Okay, so far so good. Okay, let's combine the line terms. When we combine the line terms, the coefficients won't change. See, x plus x is x. Okay, it's not gonna be 2x. We don't have an integer coefficient for it. So you see, x, y, z, we have both of them are x, y, z, so that will give us x, y, z. And let me see, do I have a different color? Okay, and then x, y, z bar. There are 3 terms of that, right? So it will also give us x, y, z bar. Will only give us 1 term. And then next, so we have then the remaining 3 terms, they are different. So let's just write them down. So far so good. So now we have 5 mini terms. And then let's translate back to and or. So this is xyz or xyz bar or xy bar z or xy bar z bar or x bar y z bar. So far so good. So you can see when we translate to like plus and multiply, we can use our like common algebra. We can calculate naturally. But when you combine the like terms, just keep in mind you won't increase the coefficients. So far so good, everybody. Okay, let's continue. So I hope you can like pause the video here and try to work on this problem. So after you're done, you can continue to play the video. Okay, are you done? So let's see. Okay, first thing, let's translate. This is x bar y. When you see or, it's like plus. Okay, what is this guy? So this is like x and z bar, or use the De Morgan's law. That is x bar or z bar. Okay, so this is x bar or is that plus z bar. So far so good, everybody. And then times, okay, what is x or yz bar? What is this guy? Well, this is the same as x bar and yz bar, right? And let's move the bar inside. X bar and parentheses y bar, because this is like and in the between, now become or. Okay, so we have x bar times y bar plus z bar. Okay, so we want to make sure that we have moved the bar into each of the variable. Then we can continue. Okay, because the or is associative, we can actually remove, because both operation is or is associative and commutative. Okay, we can remove the parentheses. The order where we add the numbers first doesn't matter. Okay, and furthermore, what is this guy? So x bar y is x bar intercept y, and then when you union x bar, because this guy is a subset of x bar, this guy is bigger, so when you take or between them, this is just x bar. Okay, so it can help us to simplify. So this is just x bar plus z bar, and then we have x bar, and then we have y bar plus z bar. Let's distribute everything. Okay, so we distribute, let's see. Distribute, we get x bar plus z bar x bar, and then we have the y bar z bar. Okay, let's continue. Well, at x bar intersection, this guy is still x bar, right? Then when we distribute, so we have x bar y bar plus x bar z bar plus x bar y bar z bar plus x bar z bar z bar. Okay, what is this guy? Oh, right. So you can see z bar together is the same as z bar. So actually this guy and this guy, they are the same. Okay, they are the same. So we can just combine them and just pick one of them. So we have x bar y bar plus x bar z bar and plus x bar y bar z bar. Okay, you see the first term we don't have a z, so let's insert. So insert z plus z bar. Second term we don't have a y, so let's insert y and y bar. Last term is good, so just leave it there. Alright, distribute it, x bar y bar z, x bar y bar z bar. Here, distribute x bar y z bar, x bar y bar z bar. Last one, x bar y bar z bar. Okay, let's see. This guy is by itself. We don't have like terms, right? So x bar y bar z. But the next term we have this guy, this guy, this guy. All of them are the same. So just put one term here. And we also have this term x bar y z bar. So far so good, everybody. Okay, and all of them are different mini terms. So we're good. Then we can change it back to or. And this is our answer. So far so good, everybody. So tips is when you see a complement over a lot of terms, better to distribute that complement over each single variables. And then translate the problem to plus and times, and then use our algebra rules. But in the process, you can also think about some properties like here. Oh, let me put it down here. Like here, we use the property that x bar y union x bar is just x bar. And actually, here there's another properties. Do you see x bar and x bar union z bar? Because this guy is the subset of that guy. When you AND it, oh, this is actually just x bar times y bar plus z bar. Ooh, so this is x bar y bar plus x bar z bar. And then let's see whether you can get the same answer. Let's see here. So the first term we don't have z, so let's insert this. The second term we don't have y, so let's insert the y. Then here we have x bar y bar z, x bar y bar z bar, and then here we have x bar y z bar and x bar y bar z bar. X bar y bar z bar are the same. We can combine them, so we have x bar y bar z plus x bar y bar z bar plus x bar y z bar. Do we have the same? Yes, it's the same. See, sometimes if you realize there's some problem about intersections and unions, you feel free to use them. It might shorten your work. So far so good. So that is sessions 11.4. Okay, and that's it for the chapter 11. So please go ahead and complete your homework. If you have questions, feel free to print screen and ask me in class or office hours or email me. All right, have a nice day. Bye.